So while I'm waiting for the time to get to be 10, I'm posting computer assignment 5 later today. Not because it's due anytime soon, but just so that you have time to look at it. Computer assignment 5, I think out of all of them, it's probably one of the ones it's my favorite. And the reason I like it is that it has to do with image processing. And the reason I like that is that it gives you like a whole new perspective on signal processing. So everything we've been doing so far, when I've shown you an image and I say take its Fourier, or not image, when I show you a signal and say take its Fourier transform, what's on the x-axis of that signal 100% of the time? Before you convert it, it's time. So we start with time signals and we take their Fourier transforms. So what's fun about the image processing lab is that instead of taking time signals, you're taking images. So what's your x-axis in an image signal? Location, samples, right? It's a distance, okay? It's a spatial frequency, all right? But mathematically, at the end of the day, it's just numbers. Sorry? Yeah, or even if you just think about one line. Like let's say you take an image and you just look at, just take a cross-section of that image, right? It doesn't matter what's on the image. So here's a cross-section of your image. So suppose every pixel in there was black. All right? What's the frequency of that? Or if it's all white or all pink or all whatever, what's the frequency of that line? It's constant, right? There's no change in the color, right? So, you know, at the end of the day, it's just numbers, right? And you take their Fourier transform, you get something. But you know, if every pixel was the same color, you can think of it as a constant signal, right? Then you can start to think, what if it was like black, gray, white, gray, black, gray, white, gray, black, and so on? What's that kind of a signal? Yeah, it's sort of like a cosine, right? Up, down, up, down. Okay, so when we look at his Fourier transform, you might expect some other kind of properties. All right, you might, in fact, when you take its Fourier transform, you might in fact see something that looks kind of like a cosine in Fourier space. But what's fun about it is that after you think about it for a while, it becomes apparent that putting time or putting space on the x-axis doesn't really change the problem at all, because at the end of the day, it's just a bunch of numbers. And once your signal is a bunch of numbers, it doesn't matter what they represent, whether it's time or pixels, you can still take their Fourier transform. It works exactly the same. The only thing that makes this assignment a little different now is that you have two dimensions, right? Because you have an image, you have x and y. So when you take your Fourier transform, you don't just have frequency. Now you have frequency in the x dimension and frequency in the y dimension. So it gets kind of trippy. It's sort of like a spectrogram. When you do a spectrogram, it gives you time on one axis and frequency on the other axis. Now you're going to be getting frequency x and frequency y. So it's also a two-dimensional plot, but it's representing or a three-dimensional plot, but it's representing different stuff. Anyway, read the assignment. It kind of explains it in a good amount of detail. I'll post it later today. But it's kind of a cool assignment. Has anybody ever dealt with aliasing on a computer monitor, like for video games and stuff? One person. Okay. Well, hopefully after today you'll know what that means. Okay. So I've made an executive decision. We're going to skip the. If you're still following along in the lecture notes, we're going to skip the lecture about the amplitude modulation. I'm not going to do it in class, but you should read it because it's really kind of a cool lecture and it shows a lot of an application of like all these things put together, which is pretty cool. So I would encourage you to read the amplitude modulation lecture, but I did kind of want to skip ahead for the reason that I just want to make sure that we're actually ahead this semester. I don't really know how that happened, but we have a bunch of lectures left to explore discrete time signal processing. So I want to not lose momentum. I want to just charge ahead with that as much as I can because there's like a whole side. Up until today, all we've been looking at is continuous time signals, right? Which is when your x-axis is continuous time, which is cool and all because the real world is, you know, continuous. It's an analog world, but when we use computers to analyze that world, computers are by nature discrete time systems, right? So It's like there's this whole other side of signal processing that deals with discrete time signals. So you kind of need to understand a bit of both. Typically, the way this course has happened is that we kind of wedge that in like the last 3 lectures at the end of the semester. But we're doing pretty well, so I'm going to just go with this, and we're going to kind of expand a little bit and see what we can get out of this. So I want to start with this. So here's a continuous time signal. And it doesn't really matter what the shape is. So if I want to get it into a computer, if I want to digitize it, right, make a representation of it in MATLAB or LabVIEW or whatever view, what do I need to do to that continuous time signal? I need to take samples. Okay. All right. So what does it mean to take samples? Basically means I'm just going to take a snapshot of this signal, right? So I'm going to say, okay, what was the value at that point in time? What was the value at this point in time? And so on and so forth, okay? So we're going to make a few assumptions. The first assumption is I'm going to take my samples at equally spaced intervals, right? I'm going to sample at a, if this is t seconds, this is t seconds, right? I'm not going to make some samples closer together and other samples further apart. Although, you should know that there are advanced applications where you can vary the sampling rate on the fly, and we can talk about that. But for now, I mean, like I would say 90% of all applications are evenly spaced. Okay? So the first question, and probably the question we're gonna spend a decent amount of time on today and Friday, is what dictates how closely together those samples should be, right? Like, do I need to have samples this close together, or do I need to have them, do I need to double the sampling frequency, right? Is that better? Better resolution. Why would I want to have more samples, like more samples closer together? Right, I would get more. Right, I'm clearly getting a better snapshot of the signal. So, is more samples always good? What's the downside of having too many samples?
Data, too much memory usage.
Too much data, right? I mean, yes.
I mean, it depends on the system. When the system is like steady, you have like, for example, a tape line. You don't need a lot of samples.
Look at Samer. Samer's like nailed this entire thing. This is exactly right. No, if the signal is not changing very much, then you can totally get by with not that many samples. But if the signal is changing a lot, would those two samples be a good representation? Of course not. So I think we can just see intuitively that the sampling rate has to be tied to, I'm just going to draw this backwards and forwards arrow to just say that the sampling rate is going to somehow be related to the signal bandwidth. Bandwidth meaning if there's like really high frequencies in the signal, I'm probably going to need more samples. So generally speaking, and just intuitively speaking, more samples means a better representation of the signal, and it means that I can pick up more of these high-frequency jiggles in my signal. The downside of having too many samples is that your digitized file may be bigger than necessary, right? So if you think about your iPod, let's say. Okay, just to make the math easy, I realize this is a little small. Let's say your iPod has 1 gig of memory, okay, circa 2003. Okay, and how many bytes in a song? In like one average track? Pick something round because we're going to divide. Don't give me 3. 5, thank you. Okay, 5 what?
Megabytes.
Megabytes?
Yeah. Not the songs I listen to.
Kilobytes, right?
Yeah. No, it's megabytes. It's definitely megabytes.
Megabytes. Even if you use a low.
The songs you listen to probably.
You're listening to a DOS file.
Well, let's see. What's audio sampling frequency? 44.1 K samples per second.
That's a WAV file, though.
Just hush. Well, whatever the file is, it's usually sampled at 44.1, even if it's like an MP3. But the MP3 does a bunch of compression to kind of wedge the file size down. But let's just do a back-of-the-envelope calculation to decide whether this is megabytes or kilobytes. Okay, 44.1 K. How long is an average song? 4 minutes. How many seconds is that? Because we got to get it in seconds, right?
That figure is only applicable for an MP3. If you want like a WAV file, it's going to be 60 to 80 megabytes.
Why is that?
Because a WAV file is completely uncompressed. Yeah. So.
Good. Let's just play with the numbers for a second and see what we get. Because I kind of want to, now that we started, I want to do this. So right now we're doing uncompressed. Okay? So this many, so 44.1 samples per second, K samples per second. A 4-minute song, that's 4 minutes times 60 seconds is 240 seconds. And how many bytes per sample?
16 if it's a CD.
16 bits, right? An average for like CD quality is a 16-bit sample, and we can talk about what that means. High def is 32. So let's say 16-bit is 2 bytes, right? Is that true? 16 bits is 2 bytes. So if we multiply all of this together, we should get the number of bytes in a uncompressed 4-minute song. Is that true? Okay, so I don't know. I'm not going to do this in my head. Maybe I am. Let's see. I'll see if I can do it on the board faster than you can do it on your calculator. 44, 2's, 88, 2, 4, 1, 6, 7, 6, 1, 7, 6, 12, 3, 1, 7, 8, 9. Boom, am I kicking your butts?
22,000.
Yeah, okay, I got a 19.3, but I rounded a few places. Okay, about 20,000 you said? About 20,000 K, right? It's 20,000 K. So 20,000 K, which is actually the same as 20 megabytes. Right? Roughly. I mean, we're rounding. You know, I'm not dotting the I. I did 44 instead of 44.1. Okay. So you multiply all that together, you get something in the neighborhood of 20 megabytes, which is uncompressed. So like you were saying, if you do a WAV file, you'd be looking at about a 20 megabyte file. That's a totally uncompressed. Now MP3 is a compression algorithm which says, you know, you can actually strip out, like, and use all these compression algorithms to make this file a whole lot smaller, and the file won't sound, the audio won't sound all that much different. Like, they basically figure out how to strip out information that your brain can't really hear anyway. So they kind of get it down to, so they use compression, and let's say we get it down to 5 megabytes. Okay, the compression is definitely not getting it down to 5 kilobytes, which is sort of why we started this argument in the first place. Okay, so an MP3, 5 megabytes. So if I've got a 1 gig iPod, and I'm getting 5 megs per song, so how many songs does that give me? 2,000? No, 200. Because two songs would be 10 megabytes. 20 songs would be 100, and 200 songs would be 1,000 megabytes, which is a gig. So this is 200 songs. Not bad. Okay. Now, suppose I oversampled the bejesus out of this thing. Okay, and instead of, so we started this conversation because we wanted to answer the question, what would happen if we had, like, why is it bad to have even more samples? So let's say for whatever reason, I said, you know, I want to make this like a really high fidelity song. It's going to be awesome. It's going to sound like you're at the concert. 50 megabytes per song. Okay? You don't really need all those samples because you can already get a pretty good representation of this thing with 5 megabytes, but you went bananas. You said more is always better. Okay? So I'm going to do 50 megabytes per song. So what's the first downside? You can only put 20 songs on your iPod. Okay? So that's kind of a drag. What's another reason why? What's another drag for your iPod? In having 200, if you make the sampling frequency 10 times as big.
They need 10 times more memory.
You need 10 times more memory.
10 times the bandwidth.
10 times the bandwidth.
I was going to say you need to process 10 times more signal.
You need to process 10 times more signal. And what's the downside of that? What's going to drain faster? Your battery, right? You've got this little DSP on your iPod that's got to process this data, okay, so you can hear it. It's got to uncompress the audio. You're going to make it work 10 times harder now, which means your battery's going to drain 10 times faster. And for what? You're not even going to be able to hear the difference, right? Because if it sounds good with 5 megabytes, it ain't going to sound that much better with 50 megabytes. So you're getting a marginal, perhaps imperceptible improvement in performance, and it means you get a tenth of the songs on your iPod, and you drain your battery a tenth as fast, and it's probably going to get 10 times as hot. So these are like real design problems. You say, well, I could just make the memory 10 times bigger. Okay, well now your thing has to be physically 10 times bigger maybe. Or you have to sell it for 10 times the price. So you're sort of in this design space where something's got to give. But I think it's pretty apparent that the name of the game is to get enough samples, but not more than you need. Right? You want to get enough samples so your song sounds nice. Right? Which, again, we argued in our case was something in the neighborhood of 5 megabytes. Okay? But you don't want to go overboard because then it's just wasteful. It doesn't buy you anything. Okay? And it's not even, it's not like it doesn't really get you anything. It's actually all downside. So you want to just hit that sweet spot and not beyond there. And so what we're going to talk about is how you figure out how much you need. Sound good? Okay. So, having said all that, let's go. Everything we do in this course is cosines, right? We're going to build everything out of cosines. So we're going to go back to basics. Well, let's just start with a cosine. And we're going to think about how many samples we need to digitize our lowly cosine. And then if we understand how it works for cosine, we understand how it works for everything because everything's made out of cosines, right? That's our strategy. Okay, so here's a cosine. And you will recall that x of t equals cosine omega t. Now, let's start taking samples. So I'm going to have a sample here, sample here. I'm just sort of drawing these arbitrarily. I don't want you to don't sweat too much exactly how they're spaced. Okay, so let's say that the time between samples is t seconds. Okay? So watch this. What time does this sample occur at? Can we say that sample occurs at time 0? Good. How about this sample? Where does he occur? T. And this one? 2t. And so on. 3t and so on. Okay? So can we say that the nth sample occurs at t equals, the nth sample occurs at time equals n capital T. Is that good? No lies? I'm still telling the truth. Okay. So I think what that means is that we want cosine of omega, but do we want all time? No. We want n big T. So we're going to call that. So I want to make a couple distinctions. Originally, this was a continuous time signal, and my variable was t for time. Now I'm dealing with a discrete signal. Remember, discrete means that it's not defined for all time. It's only defined at discrete times. And now at integer times. And my integer is no longer continuous t. It's now integer n, right? And so look at the way I denote this. This is a standard notation. When you put round parentheses, that means continuous time. When I put square brackets, that means discrete time. Okay, so if you see x of n with the square brackets, you know I'm talking about a discrete time signal. And that's not just me. That's just like the general convention. Okay?
So at different times, the sample, the period of the sample is changing? Or the sample at that particular time is that period of that particular sample you put?
I'm sorry, say that again? Just so you know, t, this does not refer to the period of the cosine. Right?
The big T.
Big T, I'm not talking about the period of the cosine. That is if it makes it a little easier, we can call it t sub s, the sampling period.
Okay.
It's the time between samples, if that helps. All right, as opposed, because I know we've used big T to also denote the period of the cosine, and that's not what I'm talking about. All right, and then let me do one more little conversion here, and then we'll sort of poke around and see what we've gotten for ourselves. If I have one sample, if one sample takes t sub s seconds, how many samples in 1 second? So if my sampling period is a quarter second, right? If there's a quarter of a second between samples, how many samples in 1 second? 4, right? So we say that our sampling frequency is 1 over the sampling period. So if I have a quarter of a second per sample, I take the reciprocal of that. That means that every second I'm getting 4 samples. So that means that I can take this and rewrite it as cosine of omega n over my sampling frequency. And just so we're clear, I can be exactly, I can also say, what's omega equal to? 2 pi f. So instead of expressing my continuous time frequency in radians per second, I could also say 2 pi f over f sub s n. It's the same thing, right? Okay. So, okay. All right, we're still on the same page. It's about to get trippy. All right, so in the same way that we expressed continuous time frequency, omega, right? So it was some stuff times t. I can do the same thing with my discrete time frequency, right? It's basically some stuff times n. So this stuff that I've boxed here, that's what I'm going to call, let me just start again up here. I'm going to call that capital omega, which is where omega equals 2 pi f over the sampling frequency, and that's my discrete time frequency. Discrete time frequency. And the units are in radians. This is radians per per sample. Okay, so let's play some games here with this. Let's see what this means. Some very interesting properties are about to emerge from this. And from those properties, we should be able to deduce how many samples we need in order to make this work. So, let's say we have a cosine let's say we have a 50 hertz cosine, and we're going to sample it at, I don't know, 250 hertz. So if a 50 hertz cosine, I'm going to sample it at a sampling frequency of 250 hertz. So let's calculate my discrete time frequency. So this is pretty plug and chug, right? Let's try this. So this should be 2 pi 50 over 250. So let's see, that's 100 pi over 250. That's 10 over 25. That's 2 over 5. That's 0.4, right? So that's 0.4 pi radians per sample. Oh, okay. What's that?
Factor out the 50 on the top and bottom.
There we go. Thank you. Okay. It's pretty cool. Should we try another one? What if we said, what if I gave you a cosine at 200 hertz, and we're going to sample it at, let me think of a good number here, 1,000 hertz. Oh, is that right? Let me see what I want to do here. Yes, I'm going to sample this at 1,000 hertz. Should we try that one? Okay. So in this case, my discrete time frequency will be 2 pi 200 over 1,000 . That's 4 pi over 10. Wait, is that? That can't be right. Can it be right? Yeah, it is right. Okay. So, lesson number 1 about why continuous time is a little zany. I took a 50 hertz cosine. I digitized it. My resulting cosine was cosine of 0.4 pi n. Then I took a 200 hertz cosine, sampled it, and the resulting signal was cosine 0.4 pi n. Now I can go and plot cosine of 0.4 pi n, right? I can go to MATLAB and say n equals 0 to 100, x equals cosine of 0.4 times pi times n, and then plot it, right? I'll get a bunch of samples, so I know it'll work. But my question to you is, if I were to show you that plot of cosine 0.4 pi n, how would you know whether I had been talking about a signal that was sampled at 50 hertz, or a signal that was a 50 hertz cosine, or a signal that was a 200 hertz cosine? You have to know the sampling frequency. If I don't tell you the sampling frequency, you have no way of looking at this and knowing whether I'm at 50 hertz or 200 hertz or any hertz, right? Because we could repeat this game over and over and over again, and I could always get 0.4 hertz. So do you wonder why, when I take the my FFT you have to tell it the sampling frequency. Because if you don't tell it the sampling frequency, it has no freaking clue what you're talking about, right? It can tell you that the frequency was, it can look at the signal and say the frequency was 0.4 pi radians per second, but it has no idea how to convert that back into hertz. Only when you tell it the sampling frequency can it make the connection that 0.4 pi radians per sample actually means 50 hertz or 200 hertz.
There's no time information there anyway. So there's
Well,
only, that's only like the
There's the samples is time.
where you kind of lose your time scale. In other words.
Right. So basically what happens is if you just take the raw signal and feed it into the FFT algorithm, the FFT algorithm can tell you that there is a discrete time frequency of 0.4 pi radians per sample. It will do that successfully. Right? But the problem is that we don't live in a world of 0.4 pi. We live in a world of hertz. So the only way to get from discrete frequency back into something meaningful, hertz, is to also tell it the sampling frequency. And then you can go back and actually figure out what the hertz was that we were talking about. Right? So if I tell you the discrete time frequency is 0.4 pi and the sampling frequency is 250 hertz, you can work this problem backwards and figure out that I was talking about a 50 hertz cosine. Okay, so that's lesson number 1. Unless you supply the sampling frequency, then the best you can do is to talk about discrete time frequency, which isn't wrong, it's just not all that meaningful in terms of like a real-world application. Good?
So here you're changing the sampling rate, the sampling frequency each time. What if you,
Okay, yeah,
when
yeah.
when you define the cosine?
Yeah.
So if you don't have that, you can't make any assumption of the sampling frequency?
That's right. Unless I give you the sampling frequency, you have no idea what was actually going on. I mean, I could have taken a megahertz signal, sampled it, and gotten 0.4 pi hertz, 0.4 pi radians per sample. Unless I tell you the sampling frequency, you have no idea. You cannot differentiate. That's why we are obliged, when we take the Fourier transform, unless you supply the sampling frequency, the best it can do is tell you 0.4 pi radians per sample. It can't do better than that. If you give it the if you give it the sampling frequency, then it can say, oh, well, I see energy at 0.4 pi radians per sample, and since I know the sampling frequency, I know that corresponds to 50 hertz, or 200 hertz, or whatever hertz. So lesson number 1, we need the sampling frequency if we wish to get from discrete time back to continuous time. But wait, there's more. So let's stick with our 50 hertz sample for a second. So I'm going to reduce my sampling frequency. Okay, so here we did 250 hertz. Let me think in my head what's the easiest way to do this. 1500, 125. Okay, so let's try this again. Right now we're going to stick with the 50 hertz signal. I'm just going to vary the sampling frequency now. So we just tried 250 hertz, and we got 0.4 pi. Did we not? Okay. So now let's take that same 50 hertz cosine, and I'm going to sample it at a much lower sampling frequency, 125 hertz. So am I making more samples or less samples? Fewer, thank you. I knew that grammatically didn't sound right. Fewer samples, okay? So I was giving myself 250 samples a second. Now I'm taking fewer samples, 125 samples per second. Okay, so let's calculate what my discrete time frequency is. So it's 2 pi 50 over 125. So let's see, that's 100 over 125. That is 4/5. Is that 8/10 pi? Okay, it's 8/10 pi. Okay, that's fun. Should we try making it a little smaller? Remember, one of the things we're trying to understand today is how few samples can I take of this cosine and still know what's going on. You with me?
50 hertz.
50 hertz. Let's not go too far. Let's start with 100. I want to work this progressively. So if I let my sampling frequency be 100, what do I have? I have pi radians per sample. And we're going to do one more. Let's sample it at 75 hertz. So 75 times 2 is 150. 150 over 125. Is it 1.2?
It's symmetrical about 100.
6/5, so 1.2 pi. Okay, that's where I'm going to stop for a second. Okay, now, somewhere in here we've crossed the line from having enough samples to not having enough samples. All right. So let's see if we can let's play this game. So just by way of example, if I tell you that omega is 0.4 pi, and I tell you the sampling frequency is 250, you can work out that the continuous time frequency in hertz should have been omega. What was it? It was omega equals 2 pi f over the sampling frequency. So therefore, if I take omega fs over 2 pi, I should be able to get my continuous time frequency back, right? I'm just putting the equation backwards. So in this case, I should be able to work out that 0.4 pi times 250 divided by 2 pi had better come back out to be 50 hertz, right? Okay. So let's see. We had, okay, so let me write it like this. So what we have here is cosine of 0.4 pi n, and therefore we can work backwards at f equals 50 hertz. So that's good. And we can do this one as well. This is cosine of 0.8 pi n. So cosine of 0.8 pi n. We work the problem backwards. We take 0.8 pi times the sampling frequency divided by 2 pi. We still get back our 50 hertz signal. So in other words, if we sample at this frequency, we get that discrete time sampling frequency. If I work my equation backwards, I'm still able to extract my 50 hertz. So that's good, right? The whole point is to be able to figure out what we had originally before we sampled. Now, let me skip to the 75 hertz case. Now I have cosine of 1.2 pi n. And believe it or not, I have a problem.
There's no problem.
Oh, there's a problem. Yes, sir.
I don't know, does it start to repeat?
Yes, I'm going to tell you why. For the sake of argument, let's just talk about the first sample, n equals 1. So in that case, I would have cosine of 1.2 pi. Is that right? Now watch this. Theta, cosine of theta. Okay, if this is cosine of theta, what's this frequency right here? What's this angle? What's the period of cosine? That's 2 pi. This is pi. And this number right here is the cosine of 1.2 pi. Does that equal some other cosine? Would you agree with me that the cosine of 1.2 pi is exactly the same as this number right here? Is it not? Okay. What number does that correspond to? Just by argument of symmetry. If this is 2/10 pi, this better be 2/10 pi. Look at what I'm telling you. I am telling you that cosine of 1.2 pi n equals cosine of 0.8 pi n. In this case, I proved it graphically for n equals 1. But you could do the same thing for n equals 2, n equals 3, n equals 4, and so on. Okay? So it turns out this is true for all n.
How are they equal?
Just make a list. I mean, just try it on your calculator, right? If you make a table, I mean, you should do this for homework, okay? Seriously. Can everyone do this for homework? N cosine 0.8 pi n. Just do it in Excel. Cosine 1.2 pi n. N equals 0, 1, up to 25. And then fill in these two columns and show that they're exactly, and you'll see that they should be exactly the same. So cosine of 0.8 pi 0 is the same as cosine of 1.2 pi 0. Cosine of 0.8 pi is the same as cosine of 1.2 pi. Right? The 0 case is obvious because it's 1 and 1. The 1 case we've just proven. But you'll find that for n equals 2, n equals 3, n equals 4, they're all the same. You see how that works? So, when we come back on Friday, we will discuss why this is not a good thing. Okay? This happens to be called aliasing, and I'll discuss what that means. But this is essentially where this falls apart. Cosine of 1.2 pi n equals cosine of 0.8 pi n. You cannot tell them apart. Hold on. Well, let me just do this example. Okay, I've got like 1 minute, and then I have to give you your quiz. No, I have to give you a quiz. Actually, you know what? Yeah, I'm not going to be here on Friday. Steinberg's going to give the lecture on Friday, so maybe I'll give him a bonus and just let him give you the quiz. And that way he has to prepare a little less lecture.
You take the quiz then.
Okay, we'll do that. Okay, so you'll take a quiz on Friday. Okay, so if you'll believe me that cosine of 1.2 pi n is the same as cosine of 0.8 pi n for all n, and it is true, and again, for homework, you're going to go and make a little Excel spreadsheet and prove it to yourself, then you have this situation. So if I have cosine 1.2 pi n, it's exactly, like number for number, the same as this value, as this cosine. Now, let's see what's the problem with that. So, we've taken a signal, we've digitized it, we thought we got this frequency, but really we got this frequency. Now, let's play the game of figuring out what continuous time frequency we had originally. So remember, we said you take omega, you times it by the sampling frequency, and you divide by 2 pi, and that should tell you what the original continuous time signal was. So let's try that. I'm tempted to put 1.2 pi here, but I can't. Why? Because it's the same as 0.8 pi. If I were to create a plot of this signal, you would have no way whether I had typed in cosine 0.8 pi or cosine 1.2 pi, because they're identical. So the natural assumption is you always assume that it's between minus pi and pi. You assume that that's the frequency. So look at what I've got here. 0.8 pi times my sampling frequency, which was, for this case, 75, divide by 2 pi. Can someone tell me what that works out to? No. I'm just doing this example. I'm just doing this example right now. Okay?
Works out to 30 hertz.
Do you see what the problem is? Look, let's back up. I took a 50 hertz cosine. I sampled it at 250 hertz. I said, hey, I've got this signal. It's discrete time signal's got this frequency. What was the cosine? What was the original cosine? Well, I applied my formula. I worked my way back. I got 50 hertz. Oh, that's correct. That's good. That means that 250 hertz is enough samples to accurately capture my 50 hertz cosine. I said, good. 250 hertz? Great. Let's see if we can shave a little bit off. Let's go down to 125. I played the same game at 125. I took my 50 hertz signal. I sampled it. I got that frequency. Okay? I said, hey, if that's my discrete frequency and that's my sampling frequency, what was the underlying cosine? 50 hertz. Again, good. That means that sampling at 125 hertz was a high enough sampling frequency to accurately capture my 50 hertz signal.
So you don't have to use the 250, you can actually use 125.
Right. So 250 is actually overkill. Right? I can actually get away with the 125. What about the 100?
Well, at that point, this was pi 50 repeated too, isn't it? Or
It turns out that you can, with this, you can just barely do it. This, as it turns out, is the magical frequency. That's why I skipped it. So let's just look at the 75 real quick. Okay, I took my 50 hertz signal, sampled it at 75 hertz. That gave me this discrete time frequency, which I then argued was identical to this discrete time frequency. You cannot tell them apart. So now I'm working off of this discrete time frequency. I worked my problem backwards, and lo and behold, I did not get 75 hertz. If I show you this, if I showed you a discrete time signal with this discrete time frequency and tell you that it was sampled at 75 hertz, the only logical conclusion you can draw is that I had sampled a 30 hertz signal. And that's the problem. I started with a 50 hertz signal. I showed you the sampled version of it, and you said, oh, well, clearly this was derived from a 30 hertz signal, which is incorrect. Okay? And that means that you did not sample at a high enough frequency. Yes?
In the case, like, let's say you had a sound, it would sound almost the same at some time, like some frequencies will be almost the same, but some other won't be.
That's okay. It's not about how close the frequencies are.
Can we try that and see how it sounds like? Do the 50 and the 30.
Yeah, we can do that. I'll have John do it for you on Friday. That'll be a nice demo.
you can't really hear. So does that mean if you plot the signal with 75 hertz sampling frequency that you're going to see something that looks like a 30 hertz?
Yes.
every time?
Yeah. And so there's a demo. Again, this is something I'll have John do for you on Friday. But essentially what you're doing is you're starting with a high frequency cosine. You're not taking enough samples so that when you go to reconstruct it, instead of being forced to reconstruct the original cosine, you're basically rebuilding a cosine that's at a lower frequency. Right? If you put more samples, then you're sort of forced to draw the original cosine again. But if you take too few samples and connect the dots that you connect are a lower frequency cosine than what you started with.
What makes it carry?
Sorry, all these awesome questions. Go ahead, Justin.
I just wanted to ask, so it doesn't matter like at what frequency the signal is if once omega crosses pi and everything?
Right. So let's just let me answer this in the 3 minutes I have left, because this really is the payoff. What's the lowest frequency the lowest sampling frequency I can get away with?
Symmetrical and it flips over. It basically starts with everything after pi.
Right. I just erased the picture. Right. So this was my cosine of theta, or I guess let's say my cosine of omega. Maybe that's easier. So what's the biggest discrete time frequency I want to have? Pi. Right. Because if I exceed pi, that's where my trouble started. Right? If I'm operating over here, that's equivalent to some frequency that's over here. And that's where I run into problems. So the biggest discrete time frequency I want to have is pi. Okay, so that means that I want my discrete time frequency to be less than pi. Discrete time frequency is the same as 2 pi f over sampling frequency, is it not? Okay, so I want that to be, hold on, I got a pi, good, I'm sorry, brain fart, I'm back. Okay, so omega we said is the same as this quantity, right? So let me massage, look, the pi's cancel, that's nice. So this means that if I solve this, It means that my sampling frequency must be greater than 2f. And that, my friends, is called the Nyquist. Sorry about the crappy marker. Thank you for bringing your marker. I am at once disgusted and grateful. This is no. I'm pulling your leg. This is the famous Nyquist theorem. Okay, if you take your signal and you want to accurately capture it, you're obliged to use a sampling frequency that is at least double the frequency of the signal. Otherwise, you have not gotten enough samples to accurately capture it. So, audio. What are the range of frequencies that we speak?
20 to 20.
Human speech ranges from, or your hearing ranges from 20 hertz at the base level to 20 kilohertz at the high end of the treble level. So when you sample audio, you're obliged to use a sampling frequency that's at least double 20 kilohertz. And that's where we get our sampling rate of 44.1 kilohertz from. It's not arbitrary. It's just enough to accurately capture the highest end of the sounds that you can hear.
But we get that 4.1 extra stuff because of filtering.
Right, we'll talk about that, right? We'll talk kind of about where that comes from when we talk about anti-aliasing and so on and so forth. There's always, you never want to go at exactly the Nyquist frequency. Like, you never want to go at exactly 2f. You always want to do a little bit extra to be safe for reasons that we can discuss. But that's basically the trade-off, okay? Your sampling frequency has to be at least double the bandwidth of your signal. And that's exactly what the intuition Samer had in the beginning, right? He was saying that if your signal is a low frequency, you can get away with a low sampling frequency, right? But if it's high frequency, you need to sample quickly, right? This tells you how to do it.
So in this case, the 100 is a perfect match.
The 100 is like right on the button. If you sampled at 100 hertz, you could just barely get your signal back. But it's an awful idea to operate right at that frequency because you're playing with fire. If your signal goes a little bit over, then you alias. Anyway, I'll see you on Monday. But John will be here Friday, and he'll have a full lecture, so plan on being here. Well, he'll have a full lecture minus a quiz. So have fun.